You've seen it, right? That brilliant, intense flash of a welding torch, literally melting two pieces of steel into one. On the surface, it seems pretty straightforward. You melt it, you join it, and it cools. But what happens after that light fades is a whole different story. A real mystery, actually. You start with perfectly flat, strong plates, and you can end up with something twisted, bent, and warped. So let's dive into this invisible battle. And that brings us right to the big question. What is actually going on inside that metal? How can something as strong as steel just decide to deform itself? Well, it turns out there's a hidden culprit at work, this incredibly powerful force that gets locked inside the material. It's called residual stress. And that internal tug of war is exactly what we're going to investigate.
Every good investigation has to start with the evidence. And for us, the evidence is the final, twisted shape of the metal itself. You can think of these shapes as the fingerprints left behind by those invisible forces. And they tell a story through a few very distinct patterns.
So, first up, we have what's called longitudinal shrinkage. As the weld bead and the metal right next to it start to cool down, they contract. This pulls the ends of the plate inward, literally making the whole piece shorter right along the weld line. But that's just one part of the puzzle.
Because that pulling action doesn't just happen along the weld. It happens across it, too. This is transverse shrinkage. The cooling metal pulls the two separate plates toward each other, narrowing the entire welded part, so it's shrinking in two directions at once.
And this is where things start to get even more complex, moving into 3 dimensions. Angular distortion. See, the top of the weld cools at a different speed than the bottom. This uneven cooling pulls the edges of the plates upward, causing them to rotate into this very distinct V-shape. Now, in the most extreme cases, and you see this a lot with thinner sheets of metal, those internal compressive stresses just get so powerful that the material can't handle it. It has to give way somewhere. And that's when you get this dramatic bending, or that classic wavy, buckled shape. Okay, so now we've seen the evidence, the fingerprints of the crime. Let's go find the culprit.
So we've seen the what, all those different shapes of distortion. But now we need to get to the why. And that means we have to dive into the fundamental physics of the material itself. It's a war of properties.
And here he is. Let's formally introduce our main suspect, residual stress. The best way to think about it is like trapped energy. Even after the metal is totally cool and solid to the touch, there are these powerful forces, tensile and compressive, still locked deep inside, constantly pushing and pulling against each other.
So how does this battle even start? Well, during the weld, the metal near the torch gets incredibly hot, and it tries to expand, but it can't. It's being held in place by all the cooler, stronger metal surrounding it. It literally has nowhere to go, so it kind of mushes. It deforms plastically. Then as it cools down and tries to shrink, it starts pulling on all that surrounding metal, and that's what locks in all that stress.
So that begs a really interesting question. Which part of the metal's personality is more to blame for all this warping? Is it the thermal properties, how much it expands and contracts when you heat it up, or is it the mechanical properties, its raw strength, how much it resists being bent out of shape? Well, some researchers designed a clever experiment to find out, and honestly, the results were not what you'd expect.
Okay, check this out. They welded 2 different types of steel together to isolate the properties, and the numbers are just fascinating. Look at that third line. When they combined the thermal properties of plain old mild steel with the mechanical strength of stainless steel, they got the most curvature, a whopping 29.5. That's way more distortion than even pure mild steel created on its own.
And this just brilliantly highlights the key finding, the big reveal. The main driver behind all that warping isn't the metal's strength at all, it's its thermal dilatation. Basically just how much it wants to expand when it gets hot. That, it turns out, was the dominant factor in deciding the final warped shape.
So we know what's happening, and we've got a much clearer idea of why it's happening. But for the engineers who build the bridges we drive on and the planes we fly in, just knowing isn't good enough. They have to be able to predict these invisible forces with incredible accuracy.
And how do they do that? They build these incredibly sophisticated computer models. These models are based on something called constitutive equations. Now, don't let the fancy name fool you. These are basically just the complex mathematical rulebooks that describe exactly how a material is going to behave under any given amount of heat and stress.
But here is the massive challenge. A material's properties, they aren't fixed. Its strength, its stiffness, everything about it changes wildly as the temperature skyrockets and then plummets during a weld. So that rulebook we just talked about, it's constantly being rewritten, moment by moment.
And just when you think you've got it all figured out, there's another hidden effect in the mix. As the steel cools, its internal crystal structure literally rearranges itself. A good way to picture it is like water freezing into ice. It's still H2O, but the molecules have snapped into a new, organized pattern. Well, this phase transformation in solid steel creates its own unique strain. It's a phenomenon called transformation-induced plasticity, or TRIP for short. And let me tell you, it's a tiny detail with enormous consequences. The models have to get it right.
So what happens if a model just ignores it? If you leave TRIP out of the calculation? Well, this is the predicted stress inside the steel. Take a good look at that graph. Really burn that shape into your mind, because what's coming next is the smoking gun.
And here it is, the crucial comparison. On the left, that's the prediction without TRIP. On the right, that's the prediction with it. Now, the curves might look vaguely similar at a glance, but the actual values, the amount of stress, are completely different. Leaving out that one little piece of physics doesn't just give you a small error. No, it gives you a fundamentally wrong answer about the forces that are locked inside that piece of steel.
Now, this might all seem like a really complex academic exercise, but the real-world stakes for getting this science right are, well, they're incredibly high. This isn't just about math. It's about safety and reliability.
I mean, just think about it for a second. We rely on welds to hold together pressure vessels, bridges, pipelines, airplanes, even nuclear power plants. An inaccurate prediction of residual stress could lead to cracks forming way too early and maybe even catastrophic failure. This science is literally holding our world together.
The complexity here is just staggering. To be accurate, these models have to account for at least six different types of strain all happening at the exact same time. We're talking elastic strain, thermal strain, plastic strain, and even that strain from the phase transformations we just saw. It's a true computational ballet.
So the next time you walk past a construction site or you're looking at a bridge, take a closer look at those weld beads. I promise you, you won't just see a simple joint anymore. You'll be seeing the result of an invisible internal battle, a solved mystery of physics that engineers have figured out how to predict and control, all to make sure the structures we depend on every single day are safe and strong.